Today I'm taking the topic complexity. So, in this seminar, I'm focusing on the complexity theory, then specifically focusing on complexity classes. So, NP, NP hard, and NP completeness problems. By understanding these classes, we gain a valuable insight into the efficiency of solving computational problems and the challenges we face in the computer science. So, introduction. What is complexity theory? Complexity theory is a branch of computer science. It is concerned with the difficulty to solve computational problems. So, it focused on analyzing the resources like time and memory required to solve problems. Understanding complexity allow us to classify problems based on their inherent difficulty. So, complexity is like a map of the computational landscape. It helps us to understand which problems are easily to solve, which are hard, and where the boundaries lie. This knowledge is crucial for designing efficient algorithms and tackling challenging computational tasks. So, first one is NP class. The P class stands for polynomial times. It encompasses decision problem that can be solved by deterministic tuning in polynomial time. So, polynomial time refers to the amount of time required to solve the problem. So, which scales proportionally to the size of the input. For example, the problem includes uh, sorting algorithm. For example, quick sort, then searching algorithm, binary search. So, P class represent the set of trackable problems. So these are the problems for which we have efficient algorithm that can find the solution in a reasonable amount of time, even for large inputs. This is a desirable property as it allows us to handle practical computational tasks effectively. So next one is NP class. So NP class stands for non-deterministic polynomial time. So it includes decision problems for which a solution can be verified in polynomial time by deterministic tuning. So while finding a solution might be difficult, verifying its correctness is efficient. Example of the NP problems includes travel salesman problems and satisfiability problem. So, NP class represent a problem where it's easy to check if a proposed solution is correct, but finding that a solution yourself might be computationally expensive. Imagine finding the shortest route for the salespersons visiting a set of cities. Checking if a proposed route works is easy, but finding the optimal route can be challenging. So next is NP versus uh, P. So, one of the greatest unsolved problems in computer science is whether NP equal to P. So, if P equal to NP, it would imply that every problem whose solution can be efficiently verified can, can also be efficiently found. So, this would have two significant ramifications for algorithm design and problem solving in various fields. So the P versus NP questions is like a holy grail of complexity theory. So it asks whether efficient verification or always translate to efficient solution finding. A positive answer would revolutionize how we approach computational problems. The $1 million prize reflects the importance and challenges of these questions. Next is NP hard problem. So NP hard problem is a decision problem is considered NP hard. If any problem in the NP class that the problem solved by a non-deterministic tuning machine in polynomial time can be reduced with the polynomial time. So the key points are verification is easy. Given a potential solution, it can be verified if it is correct in polynomial time. So next one is finding solutions might be hard. So directly finding the solution itself might be computationally expensive, especially for the large dataset. Not all the NP-hard problems are in NP. So there can be NP-hard problem where verifying a solution is also difficult. So NP completeness. So is a classification for distant problems whose solution can be verified in a polynomial time, but for which finding the solutions themselves might be computationally interactable. So, NP completeness signifies a class of problems that are not only difficult to solve directly but also serve as a benchmark for the difficulty of other problems. So, imagine you have a complex puzzle. Why it may be challenging to solve on your own. If someone presents you with a completed solution, you can verify its correctness relatively quickly. So this is the essence of NP completeness in a nutshell. So next one is uh, travels salesman problems. So we imagine a map of United States with the red dots representing the cities. So the red dot connect the dots. Red line connect the dots, forming a gratuitous path to visit each city once. So the problem is given a set of cities and a distance between them. So find the shortest possible route that visits each city exactly once and returns to the starting points. So the with delivery routes optimization, circuit port drilling, and protein flooding stimulation, etc. are the application for the travels salesman problem. So travel salesman problems is a classic example of NP complete problem. So imagine a traveling salesman who need to visit all the cities on his route but want to minimize the total distance traveled. So while checking if a proposed route is optimal can be done efficiently, finding the absolute shortest route become increasingly difficult as the number of the cities grows. This is the travel salesman problems. So next one is Hamiltonian cycle problems. Given a graph determines if there exists a closed path. It's like a cycle that visits each vertex exactly once. That is a cycle. Each vertex visit exactly once. So, the relationship to the travel salesman problems. Hamiltonian's cycle represents a potential route for the traveling salesman, but not necessarily the shortest one. So, the Hamiltonian cycle problems is another capi- captivating problem in computer science. So, it asks whether you can traverse a graph, visiting each node precisely once and returning to your starting point. While this might sound simpler than the travel salesman problem, it serves a crucial building block for providing the completeness of the travel salesman problem. So, reductions of travel salesman, the Hamiltonian cycle to the travel salesman problem. So reduction is transforming an instance of Hamiltonian cycle problem into an equivalent instance of travel salesman problem. So the method is we can create a new graph with additional edges and weight. So edge with the high weight. We can add edge between all the pairs of vertices that are not connected in the original graph and then assign them in high weight. So significantly higher than the weight of the existing edges. So here we are happening the magics because we can convert Hamiltonian cycle problem into a travel salesman problem. We do this we do this by creating a new graph that include all the original edges and additional edges with very high weights connecting any unconnected nodes. So in this new graph, finding the shortest possible route that visit all the nodes exactly once to the traverse salesman problem is equivalent to finding the Hamiltonian cycle in the original graph. So, thank you.